Hello everyone. Today we'll be talking about feature selection. What do we mean by features? Features are basically variables which are helping us either in supervised classification or in unsupervised classification. So in supervised classification, these features are supposed to help us get more information about the response, and in unsupervised classification, these features would help us decide whether a particular observation should go to a certain class or not. Okay. Now, why do we need selection? First question. See, many a times nowadays availability of data is not really that of an issue. Many a times you have lots and lots of data and you just don't know how to deal with it, how to handle this huge amount of data. So you might have thousands of variables available to you, and your job is to pick few best variables from those thousand. Now you might be thinking, why to pick? Why not use all? First of all, using all the variables is computationally very expensive. I would suggest take some data set where you have say 1000 variables and try doing random forest on that data on your laptop. You may not be able to get answer. Your laptop might actually take many hours and still don't give you an answer. So first of all, obviously you want to reduce the computational efforts. Secondly, if you have too many variables in your model, interpretability is definitely going to take toll. There is contribution from so many factors, you don't know what is actually responsible for what. So if you want interpretable models, it is better to have selected important variables only in your model. Okay. Thirdly, there might be correlation issues. So some of your variables might be highly correlated with each other, and in situations like say for example regression, this leads to multicollinearity issues. Okay, and hence you might want to retain only few variables which are not really very strongly correlated with each other. Okay, so that each of them kind of provides you with new set of information. Okay, and many times due to excess number of variables, there can be cases of spurious correlation. So you might be tempted to conclude relationship between two variables when in reality there is no such relationship. Okay, hence to avoid such issues, it is important that we select only the important and useful variables in our model. Of course, feature extraction is going to be another completely different issue. Why? Because the given features may not be enough. You might need to construct new features from the existing features to build a better model. In fact, most of the times the accuracy of the model, or basically the performance of the model, depends on feature selection and feature extraction. Okay, so today I'll be talking only about feature selection. So we are going to assume that we have many variables available with us, and from those variables we need to choose which variables should be used for modeling. Of course, some models have their own built-in algorithms to reduce the number of variables. For example, in regression, there is stepwise selection, either backward, forward or stepwise. But even at the preliminary stage, we can eliminate some variables. And how can we do that? We are going to discuss today. So in general, whenever you have some supervised or unsupervised learning problem, your response can be either categorical or continuous, and similarly your regressors can also be either categorical or continuous. Okay, so we will consider each case one by one, and then we will also consider the unsupervised case. So suppose you have continuous response and continuous regressor. Okay, continuous response and continuous regressor. So in this case, what can I do? Response is continuous, regressor is continuous. So of course, first thing that comes to mind is computing correlation between regressors and response. If we are expecting linear relationship, so correlation between regressor and response. If correlation is non-significant, we know we have Fisher's Z transform, Fisher's Z score test, which can be used to test the significance of correlation. So if correlation is 0, means if the H0 gets accepted, then you can safely remove that variable, because anyway it is not affecting the response. Of course, remember we are talking about linear relationship. If you suspect non-linear relationship, then you should not go for this simple linear correlation. Okay, this is one way. But the problem is, I might have most of my variables to be correlated with response. However, I might want to remove few of them to avoid the problem of multicollinearity. Okay, then what should I do? So one suggestion in such scenario is going with clustering of variables. Okay, we have studied clustering, but we have studied clustering of observations. So we used to have Euclidean distance or Manhattan distance or some binary type of distance, and then we used to cluster observations. Okay. Now here what we are going to do, suppose I have y and I have x1, x2, xp, p can be big. So I'll keep y aside. I won't use any information on y, but I have data on x1, x2, xp, and I will do clustering of variables on these. What is the difference between clustering of observations and clustering of variables? Firstly, in clustering of observations, we use, as I said, Euclidean distance, etc. But in clustering of variables, generally we use correlation based distances. Again, I am saying generally, you can use Euclidean distance, but it is not going to give you complete picture. So why do we use correlation based distances? Because if I have, say, variable x1 and x2, and suppose x1 has values 1, 2, 3 and x2 has values 2, 4, 6 and x3 has values 20, 40, 60 and x4 has values 2, 3, 6, then we know that x2 and x3 are actually not giving me much new information, right? Because x1, x2, x3, they are all multiples of each other. So technically, they are not giving me much new information. Whereas x4, even though its values seem similar to the values of x2, or for that matter even values of x1, as far as distance, like Euclidean distance, etc. is concerned, x4 is actually giving you something new. Okay, so if you go with Euclidean distance, x3 will never get close to x1 or x2 or x4. x3 will always stay apart. Whereas if you go with correlation based distance, x1, x2, x3 would be put together and x4 would be separated. And this is exactly what we want, because x3 is a scaled version of x1, x2. So it is not providing me any new information as such. Okay. Hence, in clustering of variables, it is better to go with correlation based distances. Now what do I mean by correlation based distances? So of course my correlation coefficient itself cannot be used as a distance. Why? For the simple reason that correlation between a variable and itself is 1. It is not 0. So what is an option? One option is go with 1 minus rho. What would be the range for 1 minus rho? Rho can be between minus 1 to plus 1. So 1 minus rho can be between 2 to 0. Right? I mean 0 to 2. When rho is minus 1, it would be 2. When rho is plus 1, it would be 0. Correct? Now your job is to check if this satisfies at least the first 3 distance properties. Triangle inequality we may leave for the time being, because clustering can be carried out even without triangle inequality. But other 3 properties you should check. Here we saw that if you have negative correlation, then the distance is high. But if I want to drop even those variables, for example, I have x5 which has values minus 1, minus 2, minus 3, and technically it is also not giving me any new information because it is just minus 1 times x1. So if you want to remove such observations also, then you can consider either 1 minus mod rho or 1 minus rho square as a distance function. So that distance would be 0 even when there is perfect negative correlation in addition to perfect positive correlation. Okay. And then by using such distance function, we carry out clustering of variables, and after finishing that, suppose I have cluster 1, cluster 2 up to say cluster 5. Suppose I get 5 clusters. Then from each cluster we are going to select only one variable. So if I have x1, x2, x5 here, x3, x4 here, suppose x6, x7, x8 here, then I would select only one variable from each cluster and drop the other variables. That's how we reduce the number of features or the number of variables. Now again obvious question arises, which one to drop? From these, which one should be retained and which should be dropped? One answer is check correlation with y. So if x1, if the correlation between say x2 and y is highest in this group, in this particular group, then retain x2 and drop x1, x5. Okay. So something like this can be done. This is when you have continuous response as well as continuous regressor. This is one method for selecting features. Next, let us go to the case where response is still continuous, but the regressors are now categorical. Okay, so we are in the scenario where I have continuous response and categorical regressors. Okay, so my y is continuous and I have suppose x1, x2, x3 up to xp. Each of these are categorical. How to proceed? Now here I cannot directly compute correlation between y and these categorical variables, but I can try to see which variables have more discriminatory power. Okay. So what do I mean by discriminatory power? Now suppose x1 takes only two possible values, 1, 1, 1 and 2, 2, 2. These are the only two possible values of x. Then I want to check whether x1 has a role in predicting y. So x1 has a good role in predicting y if value of y when x1 equal to 1 is significantly different from value of y when x1 equal to 2. Let me repeat. In other words, so what I am saying is expectation of y conditional mean given x equal to 1 should be significantly different than conditional mean of y given x equal to 2. If they are significantly different, then I can say that yes, x probably has a good influence, good in the sense significant influence on y. Okay. So what we can do? How do we check whether these two conditional means are different? Basically conditional mean means we have to check means of two groups. So you can go with either t-test or non-parametric test. For example, Wilcoxon test. Okay. If your categorical variable has more than one value, more than two categories, for example, say 3 categories, then you go with either ANOVA or Kruskal-Wallis. Okay. And if the t-test null hypothesis or the ANOVA null hypothesis is rejected, then only we know that there is significant difference. Hence, we can say that okay, this variable does have some contribution in predicting y. Getting my point? Okay. Now, how to go decide whether to go with t-test or Wilcoxon? Usual stuff. First step, you check normality. If normality is rejected, normality for y, if normality is rejected, then you go with Wilcoxon, basically non-parametric version. If normality is accepted, then you go with parametric version. Okay. Even in parametric, you have to then check variance, equality of variance. If equality of variance is accepted, then you go with standard t-test or ANOVA. If equality of variance is rejected, you go with modified versions, which are known as, say, Welch test. So in R, you have an option where you can say, okay, you don't want variances to be considered as equal. Is it okay? So I have continuous response Y and categorical regressors. So what I would do is, I would check whether conditional mean of Y is different for different groups. If it is different, then only I will go for, I will retain that variable in my model. If it is same, means if my null hypothesis is getting accepted for ANOVA, then I will delete those variables. Is it okay? Now, how many such tests you will have to perform? Either ANOVA or t-test. So you have p variables. So for each variable, you will need a test. So you will be carrying out p tests. And if that p is big, then you are going to face another issue, which we will discuss in next lecture, which is known as issue of multiplicity in testing of hypothesis. Okay. So we are going to face that issue, but we will discuss it later. Okay. Now let us go to the third scenario, where I have categorical response and continuous regressors. So if I have categorical response and continuous regressor, what I can do is, I can try something like logistic regression, but I would do individual logistic regression for each variable, and I will see which variables have significant role in predicting the response. Okay, so logistic regression can work. Another option is again going with t-test or ANOVA. So now you have x1, x2, xp as continuous and y is categorical. So suppose y is 1 2 1 2 1 2, then you carry out t-test for x1 and see if mean of x1 is different for the two levels of y. Same do for x2, same thing you do for xp, and you retain only those variables for which, so now you are doing something reverse. So now we are comparing expectation of xi given y equal to 1 with expectation of xi given y equal to 2. Okay, and if these are significantly different, then only you say that okay, these xi's can probably have a role in predicting y. Okay, so you have two options. You either go with something like logistic regression or discriminant analysis, and or you go with same again t-test or ANOVA, etc. Of course non-parametric tests also, but you have to remember the difference between earlier and this. In this scenario, in the earlier scenario, we had to check normality and equality of variance, etc. of y variable when the two classes are given by the x variable, whereas here the situation is reverse. I have to check normality and equality of variances for xi's when the classes are provided by the response y. Okay, and the last scenario is both are categorical. So both are categorical, regressor as well as response. So how do you decide which variables to use here? So categorical response and categorical regressor. So here again you can go for logistic regression. By the way, I am not necessarily talking about binary logistic. Even if you have multi-level response, you can go for multinomial logistic. Okay, so you go for logistic regression, that is one option. Another option is you go for chi-square test for association or independence, whatever you like to call it. So if I go for chi-square test of association and if the null hypothesis gets accepted, so this test you will have to carry out for each pair. So yx1, then yx2, then yx3 and so on. And you retain only those variables for which null hypothesis gets rejected. That is, you end up concluding that the two variables are associated with each other. Okay, the different levels of two variables are associated with each other. Okay, so this is in the case of categorical regressor and categorical response. What about in all these scenarios we are saying that okay, we have a response variable. What if we don't have response? Basically it means we are in the unsupervised setup. So what if I am in unsupervised setup? This clustering of variables can work even in the unsupervised setup, because we are kind of dropping those variables which are highly correlated with the current variable. So it means that they are not providing much new information. So clustering of variables can work. Okay. Another option which can work everywhere in the continuous scenario is going for PCA. So you can reduce the dimension and you can remove the correlation by going for principal component analysis. The only problem with principal component analysis is again interpretability is lost. As soon as you get PCs, your interpretability is lost. Okay. But other than that, this is also a valid option. So if you are not much concerned about interpretability, if you are just concerned about say prediction accuracy, then this can work. Okay. Whatever I have discussed here are kind of very raw or crude suggestions. There is no hard and fast rule. Okay, there is no perfect recipe. The key here is you have to explore and experiment. So you have many statistical methods with you. You have a bag of tools with you which you learned in BSc and which you learned in MSc first year. So you can use any of those tools. In fact, a simple thing like interval plot, so graphical things like say box plot or interval plot can also tell you which variables should be retained and which variables should be dropped. Okay, so exploratory techniques are always there in picture. Hence, your job is to optimally use whatever methods you have learned so far to get the best possible outcome. Means to get the best possible subset of regressors. There are some advanced methods. For example, there is something called lasso. Your homework is to go and check full form of lasso. So there what you do, again you try to reduce variables by introducing a penalty or a shrinkage parameter. So if you fit for example a regression model, then some betas, even if they are significant, if they are very close to 0, then lasso tries to set them to 0 and get new estimates again, and in that way it reduces the number of variables. Okay. So there are some such advanced methods also, but most of our basic methods, the descriptive statistics and exploratory statistics part works really well in variable selection. Okay. So please keep this in mind whenever you come across a new data set. Don't just blindly input all the variables in the algorithm and start computing whatever you want to compute. Okay, first do some exploratory analysis, draw graphs, try to get a feel of which variables are important. Then do some exploratory testing like I suggested, t-test, f-test, t-test, ANOVA, non-parametric tests, etc. Again, that should help you decide which variables are supposedly contributing more, and then once you have kind of identified a good set of variables, you try to build your final model using those. Okay, so I think I should stop here. Thank you.